Overview of enterprise networks, networking devices, routing protocols, network types, and services like DNS. Enterprise networks are designed to connect and support the communication needs of organizations. These networks rely on various devices, protocols, and services to manage data flow and ensure security. Key networking components include routers, switches, and firewalls, while protocols like TCP/IP govern how data is transmitted across networks. In the 1960s, the U.S. Defense Advanced Research Projects Agency, DARPA, pioneered ARPANET, the foundation of what later became the modern Internet. ARPANET was the first network to use packet switching, a method where data is broken into smaller packets, sent across various nodes, and then reassembled at its final destination. Connecting networks, ARPANET, eventually evolved into what we now know as the Internet, often called the network of networks, because it connects numerous local area networks, VLANs, globally, to a vast wide area network, WAN, backbone. Today, billions of devices around the world are interconnected through the Internet, utilizing the Transport Control Protocol, Internet Protocol, TCP/IP, to communicate over packet-switched networks. Advanced devices and technologies, such as routers, routing protocols, SD-WAN, the Domain Name System, DNS, and the World Wide Web, WWW, make communication between these devices seamless and efficient. Basic operations of computer networks and common networking devices. Routers are physical or virtual devices that forward data packets to destination networks along a specific path, utilizing logical addresses. They use various routing protocols to select the most efficient route to a destination based on factors like bandwidth, cost, delay, and distance. A wireless router combines the functions of a router and a wireless access point, AP, providing both wired and wireless network routing. Default gateway. A default gateway is a node within a network that uses the Internet Protocol, IP, suite, and acts as a forwarding host, router, when no specific route matches the destination IP address of a packet. It serves as an access point to other networks, often requiring not only address translation, but also a change in networking technology. Access point. An access point, AP, is a network device that connects to a router or wired network and broadcasts a Wi-Fi signal, enabling wireless devices to connect to a wireless network. A wireless repeater extends the Wi-Fi network range by retransmitting the signal from a wireless router or AP. A hub, or concentrator, is a network device that connects multiple devices such as desktop computers, laptops, and printers within a local area network, LAN. Traffic sent to a hub is broadcast out to all ports, which can lead to network congestion and potential security issues. Devices connected to a hub can receive both unicast, device-to-device, and broadcast, device-to-all, traffic from all other devices on the same hub. Switches. A switch functions similarly to a hub, but is more intelligent, as it forwards data packets to specific devices based on physical addresses. Unlike a hub, a switch directs traffic only to the port associated with the destination device, using a process called micro-segmentation. This segmentation creates isolated network segments, increasing data transmission rates within each segment. Switches are more secure than hubs because of this targeted transmission, and they can also implement virtual LANs, VLANs, which logically segregate a network to limit broadcast and collision domains.
Routed and routing protocols. Routed protocols like IP are responsible for managing packets that contain routing information, enabling these packets to be transferred across networks with the help of routing protocols. Routing protocols operate at the network layer of the OSI model and define how routers communicate with one another to determine the best path for data. These protocols can be either static or dynamic. Types of routing protocols: static routing and static routing. Routes are manually configured and updated on routers or network devices. If a static route fails, traffic cannot be automatically rerouted unless a secondary route has been pre-configured. Additionally, if the route becomes congested, Traffic cannot dynamically switch to a less congested path. Static routing is mainly suitable for small networks or specific cases, such as backup routes or destinations accessible through a single router. The advantage of static routing is that it requires low bandwidth since routing information is not broadcast across the network, and it offers a level of security, as users can only access destinations defined in the static routes. Dynamic routing protocols automatically learn new routes or alternative paths, and continuously determine the optimal route to a destination. The routing table is regularly updated with current information, allowing for more flexible and efficient network traffic management. Dynamic routing protocol classifications. Dynamic routing protocols can be categorized into three main types: distance vector, link state, and path vector. Distance vector protocol. A distance vector protocol makes routing decisions based on two key factors: distance, such as hop count or another metric, and vector, the exit router interface. It periodically updates its peers and neighbors about topology changes. However, one significant challenge is convergence, the time it takes for all routers in a network to synchronize their routing tables with the most recent link status information. Without convergence, if routers have not fully converged, some may be unaware of topology changes, leading them to send traffic to unreachable destinations. During convergence, while convergence is in progress, routers exchange updated routing information, causing the network to slow down. In distance vector protocols, this process can take several minutes. Routing Information Protocol (RIP). RIP is a well-known example of a distance vector routing protocol. It uses hop count as its metric, with a limit of 15 hops to prevent routing loops. Any destination beyond 15 hops is considered unreachable. In addition to this hop limit, RIP incorporates four key mechanisms to prevent routing loops. Split horizon prevents a router from advertising a route back through the same interface from which it was learned. Triggered updates. When a change occurs, updates are sent immediately instead of waiting for the standard 30-second RIP update interval. Route poisoning marks a bad route with a hop count of 16, effectively signaling that the destination is unreachable. Hold down timers. When a destination is reported as unreachable, a timer is started to prevent the router from accepting updates about that route until the timer expires. This mechanism also helps mitigate issues with flapping, where a route repeatedly toggles between being up and down. Link state protocol. In contrast to distance vector protocols, link state protocols require routers to maintain a comprehensive map of the entire network. These routers periodically send updates containing information about their direct links to all other routers within the network. Compute intensive. Link state protocols require significant computational power, as routers must calculate the optimal route to each destination. Considers numerous factors. Link state protocols evaluate various metrics such as link speed, delay, load, reliability, and cost. Convergence. Convergence happens very quickly, often within seconds, when using link state protocols. Use case. Open shortest path first (OSPF). An example of a link state protocol is OSPF, which is widely used in large enterprise networks. OSPF routes traffic within a single autonomous system, AS, and divides networks into areas that are identified by 32-bit area identifiers. These area IDs may correspond to network IP addresses, but can also duplicate IP addresses without causing conflicts. Path vector protocol. A path vector protocol functions similarly to a distance vector protocol, but avoids scalability issues related to the hop count limit. Each routing table entry in a path vector protocol contains path information that is dynamically updated as the network topology changes. Border Gateway Protocol (BGP). BGP is a prominent example of a path vector protocol and is used to route traffic between separate autonomous systems. Providers. BGP is the core routing protocol used by Internet Service Providers, ISPs, Network Service Providers, NSPs, and very large private IP networks. Networks and topologies. Area networks and topologies. Computer networks are typically classified into two major types: local area networks, LANs, and wide area networks, WANs. LANs. Local area networks. A LAN is a network that connects end-user devices such as computers, servers, printers, and other resources within a localized area, such as a building or campus. These devices share applications, databases, files, and other resources, allowing authorized users on the LAN to access them. LANs can be wired, wireless, or a combination of both. Common networking equipment used in LANs includes bridges, hubs, repeaters, switches, and wireless access points, APs. LANs generally adopt two main network topologies, with various variations star and mesh. Older topologies like ring and bus are rarely used today. Star topology and a star topology, each node is directly connected to a central hub, switch, or concentrator. All data communication passes through this central device, which can lead to performance bottlenecks or even become a single point of failure. Despite this potential drawback, star topology is ideal for most network sizes and remains the most widely used LAN topology. Mesh topology in a mesh topology, all nodes are interconnected, providing multiple communication paths to ensure redundancy. A mesh topology can be used throughout the entire network or applied selectively to critical components like routers, switches, and servers, reducing bottlenecks and eliminating single points of failure. WANs, wide area networks. A WAN connects multiple LANs or other WANs over a large geographic area, such as a city, region, country, or even across the globe like the Internet. WANs enable geographically dispersed devices and users to communicate as if they were on a local network. Common WAN devices include routers, firewalls, modems, access servers, VPN gateways, and WAN switches. Traditional WANs, traditional WAN architectures rely on physical routers to connect remote or branch users to centralized applications or data centers. Each router contains a data plane, which holds the traffic, and a control plane, which directs where the data should flow. This routing process is often manually configured by network administrators for each router, which can be time-consuming and error-prone. SD-WAN, software-defined WAN. SD-WAN simplifies WAN management by separating the control and management processes from the physical hardware. Instead, these processes are available as software, enabling easy configuration and deployment. With a centralized control plane, network administrators can quickly write and apply policies across the entire network. Benefits of SD-WAN 1. Simplicity with centralized management. WAN administrators can easily implement routing rules based on application-specific policies. SD-WAN also supports zero-touch provisioning, automating the deployment and configuration process. This significantly reduces operational complexity, resource demands, and the costs associated with setting up new locations. 2. Improved performance. SD-WAN enhances user experience by efficiently routing traffic, particularly for cloud-based resources, without needing to send traffic back to centralized data centers. 3. Reduced costs by supplementing or replacing expensive MPLS connections with broadband and other cost-effective connectivity options. SD-WAN reduces network expenses while maintaining flexibility. Domain Name System (DNS). What is DNS? The Domain Name System (DNS) is a protocol that translates user-friendly domain names into IP addresses, enabling users to access computers, websites, services, and other resources on the Internet or private networks. DNS functions as a distributed, hierarchical database that maps fully qualified domain names, FQDNs, to IP addresses, similar to how a contact list on a smartphone links the names of individuals and businesses to their phone numbers. At the top of this hierarchy is the root name server, which serves as the authoritative name server for the DNS root zone. DNS registration. To create a new domain name accessible via the Internet, you must register your unique domain name with a domain name registrar, such as GoDaddy or Network Solutions. This registration process is akin to listing a new phone number in a phone directory. DNS is essential for the smooth operation of the Internet. Root name server. There are 13 root name servers, actually comprising 13 networks with hundreds of root name servers, configured worldwide. These are identified as a.root-servers.net through m.root-servers.net. DNS servers are typically configured with a root hints file that contains the names and IP addresses of these root servers. DNS record types A or Quad A. The A record for IPv4 or Quad A record for IPv6 maps a domain or subdomain to one or more IP addresses. Name. The canonical name. Record maps a domain or subdomain to another hostname. MX, the mail exchanger, MX. Record specifies the host names of email servers for a domain. PTR, the pointer, PTR. Record points to a name and is commonly used for reverse DNS lookups, mapping an IP address to a host within a domain or subdomain. SOA, the start of authority, SOA. Record provides authoritative information about a DNS zone, including the primary name server, the domain administrator's email address, and the domain's serial number. NS, the name server, NS. Record specifies the authoritative name server for a given host. TXT. The text, TXT record is used to store text-based information. Internet of Things, IoT, global internet expansion with over 5 billion internet users worldwide, representing more than half of the global population. The internet connects businesses, governments, and individuals across the globe. Our reliance on the internet is expected to continue growing, with nearly 30 billion devices and things, including autonomous vehicles, household appliances, wearable technology, and more, connecting to the IoT. Additionally, there will be nearly 9 billion smartphone subscriptions globally, consuming a total of 160 exabytes, EB, of monthly data by 2025. IoT connectivity technologies. IoT connectivity technologies can be broadly categorized into 5 areas: cellular, satellite, short-range wireless, low-power WAN, LP WAN, and Identity of Things, IDoT. Cellular technologies. 2G/2. 5G. Due to the low cost of 2G modules, relatively long battery life, and a large installed base of 2G sensors in M2M applications, 2G connectivity remains a prevalent and viable IoT option. 3G IoT devices equipped with 3G modules utilize either wideband code division multiple access, WCDMA, or evolved high-speed packet access, HSPA+, and advanced HSPA+, to achieve data transfer rates ranging from 384 kilobits per second to 168 megabits per second. 4G/long-term evolution. LTE 4G per LTE networks support real-time IoT applications, such as autonomous vehicles, with 4G LTE Advanced Pro delivering speeds exceeding 3 gigabits per second and latency under 2 milliseconds. 5G cellular technology provides significant enhancements over 4G per LTE, including ultra-low latency, massive connectivity, scalability for IoT devices, more efficient use of licensed spectrum, and network slicing for prioritizing application traffic. Satellite technologies. C-band. C-band satellites operate in the 4 to 8 gigahertz range and are used in some Wi-Fi devices, cordless phones, surveillance, and weather radar systems. L-band. L-band satellites operate in the 1 to 2 gigahertz range, commonly used for radars, global positioning systems, GPS, radio, and telecommunications applications. Short-range wireless technologies. Adaptive Network Technology Plus, ANT+, is a proprietary multicast wireless sensor network technology, primarily used in personal wearables, such as sports and fitness sensors. Internet Protocol version 6, IPv6, over low-power wireless personal area networks. 6 low WPAN. 6 low WPAN enables IPv6 traffic to be transmitted over low-power wireless mesh networks, designed for devices requiring wireless internet connectivity at low data rates in small form factors, like smart light bulbs and smart meters. Bluetooth/Bluetooth Low Energy. BLE Bluetooth is a low-power, short-range communication technology designed for point-to-point communications between devices in a hub-and-spoke topology. BLE, Bluetooth Smart or Bluetooth 4.0+. Devices consume significantly less power and can access the internet directly via 6 low WPAN connectivity. Wi-Fi/802.11. The Institute of Electrical and Electronics Engineers, IEEE, defines the 802 LAN protocol standards. 802.11 is the set of standards for Wi-Fi networks typically operating in the 2.4 GHz and 5 GHz frequency bands. Common implementations include 802.11n. Wi-Fi 4 operates on both 2.4 GHz and 5 GHz bands with speeds ranging from 54 megabits per second to 600 megabits per second. 802.11ac. Wi-Fi 5 operates on the 5 GHz band with speeds from 433 megabits per second to 3.46 gigabits per second. 802.11ax. Wi-Fi 6 operates on the 2.4 GHz and 5 GHz bands, and all bands between 1 and 6 GHz when available, with speeds up to 11 gigabits per second. Z-Wave. Z-Wave is a low-energy wireless mesh network protocol primarily used for home automation applications, including smart appliances, lighting control, security systems, smart thermostats, windows, locks, and garage doors. Zigbee/802.15.4. Zigbee is a low-cost, low-power wireless mesh network protocol based on the IEEE 802.15.4 standard. It is the dominant protocol in the low-power networking market, with a large installed base in industrial environments and smart home products. Low-power WAN, LP-WAN, and wireless WAN, WWAN, narrowband IoT, NB-IoT, NB-IoT offers low-cost, long battery life, and high connection density for indoor applications, using a subset of the LTE standard in the 200 kHz range. LoRa. The LoRa Alliance is promoting the long-range wide area network, LoRaWAN, protocol as the global standard for secure, carrier-grade IoT low-power wide area connectivity, primarily for large-scale public networks. Sigfox. Sigfox provides subscription-based global cellular LPWA connectivity for IoT devices, utilizing ultra-narrowband UNB, modulation and operating in unlicensed sub-GHz frequency bands. Worldwide interoperability for microwave access. WiMAX. WiMAX is a family of wireless broadband communication standards based on IEEE 802.16. Applications include portable mobile broadband, smart grids and metering, and internet failover for business continuity. Identity of Things. IDoT. IDoT refers to Identity and Access Management, IAM, solutions for the IoT, focusing on managing human-to-device, device-to-device, and/or device-to-service/system interactions. Key aspects include establishing a naming system for IoT devices, determining an identity lifecycle for IoT devices, ensuring it can adapt to their projected lifetime, creating a defined registration process for IoT devices, influenced by the type of data transmitted and received, defining security safeguards for data streams from IoT devices, outlining authentication and authorization processes for local admin access to connected devices, implementing safeguards to protect different types of data, ensuring privacy measures for personally identifiable information, PII. Thank you for joining us in this exploration of network security fundamentals. We've covered essential concepts that form the backbone of securing our digital environments, including the importance of firewalls, encryption, and secure protocols. As we navigate an increasingly connected world, understanding these principles is crucial for protecting our data and ensuring the integrity of our networks. Remember, security is not just a technical issue, it's a shared responsibility. If you found this video helpful, please give it a thumbs up, subscribe for more insights, and share it with anyone who could benefit from learning about network security. Feel free to leave any questions or comments below. We love hearing from you. Stay safe online, and until next time, keep your network secure.